Hello everyone, and thanks for checking out my brand new YouTube channel. This is the very first of hopefully many videos to come. I plan on having project updates, product demos, and stuff uploaded here, and today I'd like to start with an update on this guy. This is my PZ-1 oscillator. This is a Eurorack module that I've been working on in my spare time for the last couple of years, and this is hopefully my final prototype. I've still got to order the final round of PCBs and a new front panel, but functionally it'll be exactly the same. So what is the PZ-1 oscillator? Well, when I first started working on this project, I wanted to build a standalone desktop synthesizer that wasn't modular at all. You can see the first iteration of that synthesizer in breadboard format in this picture here. After talking about the project with others though, I decided to change it to a modular format, so I went with Eurorack. From the start though, I wanted this module to be a plug-and-play synthesizer, which is why I included the 5-pin DIN MIDI connectors right on the front there. If this is your first Eurorack module, like it is for me, then you can have fun playing it as a standalone instrument with no other modules, but you can get more out of it by taking advantage of the CV inputs and outputs on the side. This module can also be used as a straightforward MIDI to CV converter. It's got outputs for volt per octave pitch, velocity, pitch bend, mod wheel, and aftertouch. It also has a volt per octave input, so the synthesizer part of it can still be used with other Eurorack modules without the need for a MIDI keyboard. Anyways, let's talk more about the synthesizer inside of this thing. So from the start, I wanted this module to be a digital synthesizer using primarily discrete logic components. The first iteration was a wavetable synthesizer, and the main board actually looked like this. In this iteration, incoming MIDI data would change a master clock rate, and it would cycle through waveform sample data stored on these two big ROM chips. This circuit worked, and it was actually used in the intro music that you heard at the beginning of this video. But it had some issues that I wasn't happy with. Mainly, when new MIDI data came in, the master clock would have a setup time of several milliseconds, which would manifest in the audio as a sort of key click sound. Well, this was sometimes a pleasant sound, it was also sometimes undesirable, and there wasn't an easy way that I could find to eliminate it. This version also didn't have any kind of working volt per octave input, and some of the other features which I've added on the latest version. Following this version, I redesigned the entire circuit, which added a lot of additional components, so I decided to convert the project to FPGA. The FPGA can emulate logic functions and would replace the majority of the chips that I needed. However, this was also right at the time when supply issues started occurring in the electronics industry, and those FPGAs quickly became unobtainable. So instead I went back to using discrete logic chips to make the entire circuit, and I'm kind of glad I did, because that was what I really wanted to do in the first place. Digital logic circuits are my favorite branch of electronics to work with, and I think it's kind of a unique thing to see a synthesizer designed this way in modern times. So instead of one PCB, the circuit is obviously now housed on two PCBs, just because I physically ran out of room. This design now uses a fixed master clock and has two free-running phase accumulators. Instead of the two big ROM chips storing sample data, this version takes the most significant bits of those phase accumulators, converts them to an analog signal, and then uses some other small circuits to convert them to the other waveforms. Anyways, let's go ahead and plug this in, and then I'll show you what it actually sounds like and does. Okay, so let's take a look at the controls. So the three knobs to the top right here are the same as the ones below it. This is just for Oscillator 1 and this is for Oscillator 2. It is a dual oscillator synthesizer. So this one here is going to be for tuning. This one here is a color knob, which kind of changes the waveform a little bit. And then this one here is the volume. So I'm just going to go ahead and plug in my Arteria keystep MIDI keyboard here. So I'm just going to plug that into the MIDI input. So I'll go ahead and turn up the volume on the first oscillator here. And as you can see, we can play this right away. When using the MIDI input, the PZ-1 connects its internal envelope generator to its VCA stages. The internal envelope is a simple attack and release envelope with a set attack, but the release can be adjusted using an internal trim pot. You can also bypass the internal envelope generator by plugging in an external envelope signal to the envelope inputs. The internal envelope is also velocity sensitive. You can also see that adjusting the pitch bend and mod wheel will affect the signal right away as well. The tuning knob here can be used to adjust the pitch of the oscillator. And the pitch of the oscillators can also be modulated by CV using the inputs for Oscillator 1 mod and Oscillator 2 mod at the top here. Now let's cycle through the 8 waveforms. So first we have a triangle wave, we have a sawtooth wave, that's a square wave, and we also have a noise input, or a noise waveform. This is actually a digital noise waveform generated by a linear feedback shift register circuit. The pitch of the noise is just completely independent of what you're playing on the keyboard. It's just a set noise. Moving on, we have 4 resonant waveforms. These waveforms use a square wave at 2 octaves up mixed in with your typical triangle, saw, and square waveforms as well. And this last one is actually an octave down mixed with 2 octaves up. You can also mix those waveform shapes with a low-pass filtered triangle wave by adjusting the color knob. So here's what that sounds like. The oscillator color also has its own CV inputs, so that can be modulated with control voltage inputs as well. The first oscillator also has a sub-octave, which can be turned on and off just by pressing this button. The sub-octave itself is a triangle wave, just an octave below the pitch that you're playing. Let's add in the second oscillator now. You can of course change its waveform shape independently of the first oscillator as well. We can also use the Oscillator Sync button to sync the second oscillator to the first. So whenever the first oscillator waveform starts at its 0 degree point, it will force the second oscillator to reset as well. The tuning knob for the second oscillator, however, will still affect the pitch, which can create some interesting timbral sounds. So let's go ahead and turn down the volume on the first oscillator. And now we'll turn on the Oscillator Sync button. And then let's adjust the oscillator to tuning while our first oscillator is causing it to reset because they're in sync. And then we'll hear some different timbral changes of the second oscillator. I'm just going to have my Arturia run a little sequence here. And now let's adjust the tuning a bit. Let's go ahead and turn the first oscillator back on, and then we'll go ahead and turn off the Oscillator Sync. We can of course use the tunings with the Oscillator Sync off, and that'll let you adjust that kind of detune sound. You can also just use it to force them in tune when they're pretty much close. Now let's take a look at our last two knobs here. So we have a Portamento control. And we also have a filter knob. This is a 2-pole analog low-pass filter. It is resonant. The resonance is adjustable by using an internal trim pot. And then the filter cutoff can also be controlled by CV using this center input here. Looking at the other inputs and outputs, we have a volt per octave input. So yes, you can use this with other Eurorack modules, and it can control the pitch. If I plug this in, right away you'll notice that it's going to disable the internal envelope, and our output VCAs will just be set so that you'll hear a constant drone. And if I plug this into our volt per octave output, it'll essentially, we're using MIDI to generate a volt per octave output and then putting that right back in and using that volt per octave to run our oscillator and select the new pitch. There are trim pots inside to adjust the volt per octave input and output, so you can adjust the range of the output. If it's not quite reaching a maximum of 5 volts, you can adjust it to go a little higher or lower. And then your volt per octave input, you can adjust both the range and an offset to tune it into the right kind of value for you. This is fairly close at the moment, but it's a little out. The nice thing about having the MIDI input is you get a nice big range of octaves. And at the bottom here we do have all the outputs for other MIDI functions. So we have velocity output, pitch bend output, mod wheel output, and aftertouch output, along with the volt per octave output. So with these outputs here, these 5, you can use this as a standalone MIDI to CV converter, so you can control other Eurorack modules, and you can use these while simultaneously using the synthesizer built into here. So you can have this running the PZ-1 oscillator and adding in, say, a second Eurorack oscillator to have them both playing the same pitches, which could thicken it up and make it sound really cool. But anyways, I hope you've enjoyed that. This is kind of what I've been working on for a long time. It's very close to being done, and I'm just pretty happy with how it's turned out, because I've basically just got a full-fledged mini synthesizer that's using discrete logic, something that's a little different. It's not just a clone of another analog synthesizer or anything. This is all just an original circuit that I thought was really cool, and hope you guys thought it was cool too.